Good afternoon, everybody. This is Mr. Gruber. This is our last lesson in energy. Woohoo! And I bet you're excited to start it. Corona, you excited? My buddy Coroni's here.
I think that.
Haha, he's never excited. This is the last one. Get this one done, and then we'll give you a couple of days off, and then we'll start waves in a couple of days. But let's get right to this. Now we got to bring in the whole concept of internal energy, and we need to realize something very, very important, and that is internal energy is not mechanical energy. It's not mechanical energy. So we have to come up with a different equation now. And I want you to remember this. In every problem we've done so far, we said that total mechanical energy before was equal to total mechanical energy after. That's not the case anymore. Now, the total mechanical energy before is going to be greater than the total mechanical energy after. So the question I have is, how do we make them equal to each other? Let me just move this over. Come on, move. Come on, move. So before is greater than after. So we have to come up with a new equation. And this is what we're going to do. Essentially, you're going to do this every time. PE plus KE before equals PE plus KE plus Q. That's how we make both sides equal. If you notice here on the left, I'll highlight this in this nice color here. A little thick. So here, we're saying that total mechanical energy before is greater than after. So to make them equal, we say this. Let's do this in yellow. Oh, come on, yellow. Come on. The PE plus K before is equal to PE plus KE plus Q after. So let's do some mathematical problems first. Then I'll go to some more qualitative problems. I'm going to skip one right now. And I'm going to go to something like and I think I'll skip number 2 also. I'll go to number 3. So notice it says here, it says a box at the top of a rough incline. So let's build our incline. I'll put the incline right here. So here is our incline. And it's talking about a box. Here's a box at the top, and we have a box at the bottom. So we got up and so the box at the top of the incline, it possesses 981 joules more PE. So up here we have a PE equal to 981 joules. It says then it does at the bottom. Okay, well that's easy enough because guess what, we're going to make PE at the bottom. We're going to make that baseline. So we're going to make PE at the bottom 0. All right, and then it says that the box slides to the bottom of the incline. 245 joules of heat are produced. Okay. So let's show you how we set this up using a new equation we just came up with. Now, we could start with the one highlighted in purple, but I'm going to start with the one highlighted in yellow and start right here. I'm going to say PE before plus KE before equals PE after plus KE after plus Q. Now, you saw this 245 joules of heat? That's your Q. I'm going to put that in right here. 245 joules right there. Now, it also said that the box at the top of the incline had PE. Well, we'll start it from rest. They didn't say it starts from rest, but we'll make this an assumption at the top of the incline. So this is not, these B's are not bottom. These are before. These are before. So the KE before is 0. There's no KE up here at the top of the incline. Right? So all we have before is PE. And then at the bottom, since we said PE is 0, well, there's no PE after. So notice what we did here? Let's clean this up. We essentially have PE before equals KE after plus 245. See that? So here's our next equation. I'll put this in a box so it looks nice and neat. And now I'll plug in numbers. The PE before was 981 joules. We're solving for the KE after. And we have that 245. So all we got to do is subtract 245 from both sides. 245 from both sides. So 981 minus 245. And you got 736 joules. There you go. So your KE after equals Goes a little arrow here. So KE after equals, that's supposed to be an A, 746J. Easy enough. Not too bad, right? Cron, you think that was easy?
I don't think so.
Come on, it's easy, dude. Let's go to number 4. Let me scroll up a little. See what we're going to do here. Scroll up. As shown in the diagram below, a student exerts an average force 600 Newton on a rope to lift a 50 kilogram. I'll go back to work. I'm going to skip that one. That's a work one. Let me go, because I'll show you how work gets put in. Number 5 is similar to one we just did. So why don't you guys try number 5 and then come back. Remember, see if you can figure out where the beginning is, where it starts, where it ends. And based on where it starts and where it ends, you can apply that equation we just talked about, which was PE before plus KE before anything happens equals PE after plus KE after plus Q. All right, you guys pause the video, go try it. Hey, welcome back. It says a box weighing 40 newtons is released from rest on an incline 8 meters above the horizontal. As soon as you see we got something with a height, right here, boom, we have a PE at the top and we have a KE at the top. So that's our before. All right, starts from rest, KE is 0. So PE is given. We have PE, so there's no KE before, get rid of that. Then it slides down to the bottom. Can't make my box straight, it's more trapezoidal. Come on, keep these boxes straight. So you'll see it's the same exact problem. It's at the bottom. So at the bottom of the hill, there is no PE after. All we have is KE. So now we just plug in what we have. Now, we didn't have numbers like before. We actually have 40 newtons. Hey, what's that 40 newtons? That is your FG. So that's your MG term. And that's your H right here. So there's our MGH. MGH equals KE after. They're asking for the KE. So now they're asking for velocity. So I could leave it as KE after. Plus, and they gave us a Q. I'll write it here as Q for now. Now I'll plug in my numbers. For mg, the whole mg is 40 newtons. Height is 8 meters. Equals whatever the ke after is, plus our q. It said 50 joules of heat is generated. That q is heat. 50 joules, right here. 50 joules of heat added. So 40 times 8 is 320. Equals KE plus 50. Subtract 50 from both sides. 320 minus 50. Boom. 270. So your KE after equals 270 joules. That's it. Real simple. Let's go on to the next one here. It's on the next page. I'm pretty sure at the bottom now. I'll just check. Number 5. Yep. The next one. Let's see what we're going to do here. Oh, let's see. Which ones we want to do? We want to do all these. All right, we'll go to this. We'll get qualitative later. Number 6. Number 7 is work again. I'll get to that in a second. Number 8. Block sliding down the ramp from a height of 3 milligrams reaches the ground with a connection of 50. Oh, okay. This is a simpler one. They ask you for work done by friction. Let's go to this crayon one. We need the work done by friction. Now, but you got to realize we're going to use, when we do work done by friction, that's going to be synonymous with Q, right? Because friction is just going to heat everything up. So that's all they're doing here. It's a box sliding down a ramp. So we have our ramp. I'll build my ramp here. Here's our ramp. A 2 kilogram block. So up here it's 2 kilograms. 2 kilograms. Height of 3 meters above the ground. So we got 3 meters. 3 meters. And reach the ground with a KE. So here, you know what we're setting up for. Top, we have PE before plus KE before. It's starting from rest. All right. We'll just assume it does. It slides down. All right. So we got a PE before. We hit the bottom. When it hits bottom, actually, let me go back to crayon. All right. At the bottom, we have PE after plus KE after. And don't forget that good old Q. Now, it's at the bottom. There is no potential energy because there's no height. So we're setting our PE before equal to our KE after. You're seeing this a lot. I think this is 3 in a row. This seems to be a trend. They like to do this a lot. Plus Q. Except this time they didn't give you the Q portion. They gave you the kinetic energy portion. and they want the work done by friction. So you're really just finding Q. So at the top, we have an MGH of 2 kilograms times G of 9.81 meters per second squared times a height of 3 meters equals 50 joules for the KE plus Q. All right. And I'll sit there. We do our calculation. 2 times 3 times 9.81. Did I get that right? That's 6, yeah, about 58.9. So we got 58.9 joules equals 50 joules plus Q. Subtract 50 from both sides. You get a Q of about 8.9 joules. We look at our choices, and dun dun dun, sure enough, choice 2 is 9 joules. That's a work one, number 7. Let me see. I want to try number 9. Okay. Oh, yeah. Is that a work one? We'll get that in a second. I'm going to try. Let me just check the last page. I'm not going to do all of these. Save a little time. That's an oldie one there. And, oh, I'll give you this one right here. This one, I don't know if you're going to be able to do this. But I'm going to let someone, there's got to be someone out there that can figure this one out. All right? So, you can read this one. It's number 23, the last problem here. It's a pretty dang cool problem. It's a really tough problem because it brings in centripetal force, right? And centripetal acceleration, right? It wants to know if this block will make it around a loop. That means it has to stick to the track when it gets to the top of the loop. So that's something for you to do on your own. If anyone wants to try, that's a nice extra credit problem right there, number 23. Take a picture of it and put it up, upload it to Google Classroom. All right, let's see. All right, let's go back to that first page we were doing, which was right here. All right. And let's try number 4, which brings in the concept of work. All right, let me see. Okay, because they're going to do work stuff too. So it says, as shown in the diagram below, a student exerts an average force of 600 newtons. 600, come on, give me my color. 600 newtons on a rope to lift a 50 kilogram crate a vertical distance of 3 meters. All right, so it says, compared to the work done by the student, the gravitational PE gained by the crate. Well, that's actually easier than I thought. This is probably a misplaced question. They just give you lots of information. So the first thing I want to calculate is the work done by the student. Let's change this color to, I don't want to use this crayon one. Let's see, let's get a different color. We have a blue. Let's go with the dark green. Here we go. All right. So up here, work done by students. That's going to be the work in. Now, work in has to be fin din. Remember fin din? So work in equals fin din. And by the way, if you didn't pause this, pause it now. Try this problem, then come back. Hey, you back? Okay, here we go. Let's get the work done by the student. So the force in by the student is this 600 newtons. So he put in 600 newtons. And he moved at a distance of 3 meters. It is a single pulley, so distance in and out are the same. So it's 600 newtons times 3 meters. That's a win equal to 3 times 6 is going to be 1,800 joules. Okay, so they're asking you to compare win to PE. All right, so how do we get the PE for that box? The PE, simple enough. It's a 50 kilogram box. So you got your M of 50 kilograms. We have our G of 9.81 meters per second squared. And we have our H of going up 3 meters. What do you see for PE? PE, 50 times 9.81 times 3. 1471.5, so about 1472. Ooh, what do you notice? Work in is more, so it can't be exactly the same. One is out. All right, if you subtract them, that'll tell you 1,800 minus 1472. Hey, 1472, that number rings a bell. What number is that? No, that's not the number. It's close to the number. There's another number. What was I thinking of? There's another trivia question. All right. 320. Okay, so I'm going to get about 328. So the work in is about 300 more. But you got to be careful on it. It says, oh, wait. Read the question carefully. It says, compared to the work done by the student, the gravitational PE gained by the craters, the PE is less. So it was asking in terms of the PE. So the PE is 330 less. Be very careful on that one. All right. Any more work ones? Let me see. Going back on technical. Before I go back to the qualitative stuff, which is the top there. Let me see any more work ones. Next page. Was this one a work one here? Yeah, let's take a look at number 7. Then I'll go back to 6. So once again, you try number 7 on your own. And then see if you can do it. And if you see if you can get the answer right. The answers, of course, are at the bottom of your sheet. You could check it out easily. All right, so pause this and come back. Hey, welcome back. Corona, you happy to see everybody?
No problem.
Why does it make me laugh? I don't know. Because this is crazy. I'm teaching an iPad thinking I got 20-something students in front of me and Corona.
Unfortunately not.
Okay, let's see. So it says a block weighing 15 newtons is pulled to the top of an incline that is 0.2 meters above the ground. So notice right here we have a height, right? We have a 15 Newton block. So once it's up here, the 15 newtons is going to enable us to get a PE at the top. All right. All right. Let's see. And what's it? If 4 joules of work are needed to pull the block the full length of the incline, how much work is done against friction? Oh, okay. So here's what's going on. Do you remember how in the past we had work in equals work out plus work due to friction? Well, it's a variation on that. And if you want to do this in pieces, you can. Like, for example, we have, if we want to just look at it this way, okay, work in, right? Because it says 4 joules are required to pull the block. So work in is 4 joules, right? Now, if there's no friction, all right, that's a mess. Hold on a second. Here we go. If no FF, work in equals work out, which in this case, the work out is going to be whatever PE you give it. Because remember, X work equals X energy. Remember that. All right. Well, that's only the case if there's no friction. So let's see. Work in is 4 joules, right? Well, let's see how much PE it had. Or has at the top. So PE at the top equals mgh. Now remember, they gave you mg as one thing. That mg is 15 newtons times a height of 0.2 meters. Let's see. So we get 15 times 0.2. 15 times 0.2. Oh, notice that. We get a P at the top of 3 joules. Notice. So work in equals whatever work out we have. In this case, is going to be PE, right? PE plus work due to friction, or call it Q, either one. So 4 joules in equals 3 joules of PE plus the work due to friction. So you see the loss. We got work due to friction of 1 joule. Okay, so it's going to be 1 joule of work lost. So internalize that. Work in equals work out if there is no friction. If there is friction, then you're going to lose some energy. So you saw we put 4 in. We got, I could use a highlighter here. We got 4 in. We're only putting 3 out in PE, which means left over 1 joule. Wow, I just discovered that I could use that. It's actually really interesting. I usually don't like to use it in class because when you print up notes, it will cover up, like when it prints out, you'd only see yellow. You wouldn't see the numbers under the yellow. Okay, let's see. Anything else here in these numbers that I want to do? I want you to try numbers 10 and 11 here. And actually, we can do a couple of these. What I like you to do is think, this is a good thought problem because it ties together several things we've done in the past, right? Believe it or not, it ties together conservation of momentum and conservation of energy. So see if you could read this problem, pause the video, and try some of these, and then come back and see how it's done. Hey, welcome back. Caroni, everyone's back. Aren't you happy?
Okie dokie.
Ah, he's happy now. See, for once he's happy. Let's go back to it. We got blue there. Let's go to red. So, now this is when this was on at Regents one year, this was back in 2003. It was really crazy. Okay, it says 50 kilogram child running at 6 meters per second jumps onto a sled. All right? And it says calculate the speed of the sled with the child after it jumps on the sled. And it's like, wait a minute. How am I going to get this speed? Am I using VDAT? Am I using FBDs? Am I using FatMav, conservation momentum, or energy? Well, here's the giveaway. We have a mass of 50 kilograms, all right? And he's running at a V, a velocity of 6 meters per second, all right? So we have a V. We got an M. And then jumps onto a stationary sled. So we got M. So I want you to notice something. We're starting to set up with an M1. We got an M2. We have a V1. And we have a V2. It said jumps onto a stationary sled. So we got a V2 of 0. And then it says calculate the speed of the sled with the child after it jumps on the sled. Did you figure out what that one was? This is conservation of momentum. This is cons of mom. But it's a funny thing. It is a lock together problem. This is one of the most creative lock together problems I've ever seen on the Regents. It's locked together. Check this out. We got M1 V1 plus M2 V2 before collision equals the child's mass and the sled's mass together as he's locked on the sled or she's locked on the sled times some common V. Now, the V2 before is 0, right? So M1 is the kid running at 50. Yeah, I'm going to leave out units. I shouldn't. You better put your units in. 50 times 6 equals 50 plus 10 V. So we got 300 equals 60 V. Oh, V is equal to 5 meters per second. Okay, there you go. All right. So that was just to get a V, a nice creative way to calculate a velocity. Next one asks you a simple problem. What's the KE of the sled with the kid on it? Oh, it is a she. Look at that. It is a she. Well, that's an easy one. You got a mass combined, and you have a velocity. So the mass combined is 60 kilograms. I'll use units this time. And then the velocity of 5, remember it's combined velocity, quantity squared. 5 squared is 25, times 30 is going to be 750, I think. 60 times 25 divided by 2 is 750 joules. All right, so KE is, now this is the important thing, KE equals 750 joules. And it says, after a short time, the moving sled with the child aboard reaches a rough level surface that exerts a constant frictional force of 54 newtons on the sled. It said, how much work must be done by friction? Well, this is another tough one. Notice it's a one-pointer, so you don't have to actually do any work. You could just come up with an answer. And it turns out it's actually a very easy answer. Most people thought, okay, work done by friction has to equal force of friction times distance. Where's D? There's no D given. It's very simple. It's actually very simple. If you remember, we told something a long time ago, or you could do it from here. We have work in equal. We're starting off with KE, right? So essentially, and this is you realize we did an equation a couple of weeks ago. We said work net was equal to the change in KE, right? Or you can think of it this way. If you have XKE, friction must do X work to stop it. Or it's actually this. Remember how we said work done by friction is also Q? Well, essentially what we have KE initial or KE before equals KE final, remember it's going to stop, plus Q. Now, I kind of left out the PE on both sides, PE plus, because there is no PE, right? The sled's on a horizontal surface, a rough, level surface, so there is no PE change, so I would get them out. So it's just KE before equals KE after plus Q, right, is after. So what is it before? 750 joules from question number 10. equals 0 plus Q. Oh, look at that. Q just has to equal 750 joules. That's probably a simple problem, but it's tough for a lot of people. We got to think. If you got X amount of energy, you got to do X amount of work against friction. Or somebody's got to do X amount of work to stop it, right? Okay, so I'll finish off with the qualitative ones that I left out. We'll leave these. I don't want to do number 11. I'm not going to do I'm not going to do page 37 here. All right. I think we've done enough work. The rest of the stuff you could do, you can go look on. You could look on Castle. I'm going to do a Castle assignment. All right. Where was it? Oh, the qualitative stuff right here. Here. Is it? Is this it? Yeah, I think this was it. All right. Let's try these 2 qualitative problems. Just get my eraser here. Erase this extra junk. All right. So, wet saw. I'll look up a video for a wet saw and I will put it up for you. All right. Which even explains why a wet saw used to cut through fine optical crystals is constantly lubricated with oil. A wet saw has either oil or actually water. It'll have water lubricating the saw the whole time. All right. Now, they set you up simply. All right. They talk about lubrication increasing or decreasing friction. Well, if you think lubrication increases friction, you're nuts. Lubrication decreases friction. That leaves... Oh, don't do that. Come on. Dang it. Sorry, guys. One little sweep with the hand and look what happens. Hold on. Give me a second. So annoying. Look at these beautiful notes. I use more colors at school. Nothing there. Let's see. We're almost done. Almost there. Come on. There we go. Okay, so here we are. So we know lubrication decreases friction. Now, so by decreasing friction, does that minimize internal energy or maximize? Well, decreasing friction means, remember, friction heats things up. So if you decrease friction, that's going to minimize. So decrease friction. Oh, you kidding me? You got rid of all my dang colors, right? I got to be honest. This program gets... It's you know what it is? It's the pen, because I'm using the pen. And if my palm hits... If the pen hits before my palm, whatever. Okay, enough. All right, get that there. We had the blue here. Blue, make it a little smaller. We had the green. And we had the highlighter. There we go. Okay, where were we? All right, back to the red here. So, we're decreasing friction and minimizing internal energy. So I'll put a wet saw video up for you guys. Let's look at number 2. And you could read it too. Pause it, read it, and come back. Hey, welcome back. When a force moves an object over a rough horizontal surface. Okay, so now here's the deal. So we have a rough surface. Now it says horizontal. All right, that means they're trying to look for if you're going to fall for number 3, which is an increase in PE. Can't be an increase in PE because there's no delta H. Hasn't changed height. Right? And it says constant velocity. Constant velocity means no change in, well, KE's not here, but that also means no momentum. Because remember, momentum is mv. So if v is constant, mv is constant, no change in momentum. No change of weight is just stupid. But what happens if you drag something along a rough surface? Well, that's your increase in internal energy. Never forget, and I've forgotten them, Marty McFly Williams. Never forget him. You saw a kid dragged along a rough surface as he fell off his skateboard. That's your increase in internal energy. Now, I think it was one on the other page there. Should we look at that one? All right, you could try this. Pause the video. Come back. Welcome back. Constant force used to keep a block sliding. Constant velocity right here. All right. Horizontal, setting you up. So horizontal means, it says, we're looking for an increase. It can't be PE. There's no delta H. All right. So it can't be this one either. And, of course, it says constant velocity, so it can't be kinetic energy. Can't be kinetic energy here. So process of elimination, it is number 2. All right? All right, rough horizontal track. As soon as you drag something rough, never forget. All right, rough horizontal track. Rest in peace, Marty McFly.